right, so how many of you have taken linear algebra already? By any chance? Well, those of you already know that vectors are not just arrows. Vectors can be anything, provided they meet certain conditions, you know? Well, it gets weird, I know. But for our purpose here, vectors are going to be directed line segments that have both magnitude and direction. So how are these different from the quantities we already work with? Well, number one, we need to distinguish between two kinds of quantities. Number one, those are scalars and vector quantities. Well, believe it or not, you have already worked with both of them, but mostly with scalars. For instance, some function f of x equals to x cubed plus 5. You know, this is a scalar quantity. This is a scalar function. What do? Input, output, all the bells and whistles that are related to a function, you know. But that's it. You input x, you output y, without pretty much any meaning in terms of comparing it with vector quantities. Because what are real life examples or science examples, if you will, for scalar quantities like volume, 75 milliliters, that's it. 3 hours, that's it. However, when it comes to other physical quantities like distance, 5 meters, okay, or velocity, 75 miles per hour, right? Well, but that doesn't tell us much. We need extra information about that quantity, because suppose I am at a given point here. So 5 meters in that direction, it's not the same as 5 meters in that direction. I would end up with two different positions. So here is where the vector quantity comes into play, where the direction comes into play. And well, number one, how do we represent these functions? Well, for instance, for a velocity function, usually we do v with an arrow at the top to indicate that this is a vector function, and typically the variable is t, and say t squared comma t plus 1. Another notation, that's t squared in the direction of I plus t plus 1 in the direction of j. We will learn what's that I and j with the hat representing. In the end, these are just standard vectors, all right? Another type of a vector function, that is a vector field denoted with a big F or a big G, depending we have more than one. And these functions are typically 2 variable or 3 variable functions. F of x, y, z equals to, say, e to the x squared plus z comma x, y, z, and say x squared y cubed plus, I don't know, sine of z, you know. I'm just throwing up some random functions here, but actually they're how are these two functions different? Well, these big F functions, we're going to learn them somewhere about halfway through the course. So these are functions that will at the end of the course, right? Almost in the last chapter. These are vectors that describe many vectors at the different points, as opposed to the first function. It's a vector valid function that describes the position of an object at different values of t. And typically this t is time. So the position of a particle, or rather the velocity, since this is v in this case. So the velocity after 5 seconds, the velocity after 17 seconds, the velocity after 59 seconds, you know. So, but okay, so, but what about those vectors? I think we need more about what these vectors are. So these quantities are technically free quantities, and they're not tied to a particular location. Well, what does that mean? Well, so check this out. Suppose we have this Cartesian plane right here, and I'm going to plot the point 1, 3, 3, 2. All right, this is the point 3, 2. So the point 3 comma 2 is 3 comma 2. There's no way to move that point somewhere else. If you move that 3 comma 2, say by 0.000001 unit in either the x or the y direction, positive or negative, it's no longer the point 3 comma 2. It's another point, a whole different point. But what about vectors? Okay, vectors are different because, okay, so although actually some textbooks and actually linear algebra represents vectors like order pairs. In this case, we're not going to use the order pair version, so and that's why they may look alike. They may look like the same thing, but they're not. For instance, I'm going to represent this arrow here. I'm going to represent the vector with an arrow, all right, where we will have the tail and the head. The tail is the initial point, and the head is the terminal point of the vector. That's how we will represent these vectors. All right, and likewise, I'm going to move 3 units in the x direction and 2 units in the y direction. In a similar way, I plotted this point right here, right? So 3 and 2, right? But how is that different? Well, so let me represent the vector using vector notation. That is, the vector v with angular parentheses, not with the regular parentheses, 3 comma 2. So that's number one of the differences, the parentheses and the angular brackets or angular parentheses. So, but again, keep in mind that if you read other multivariable calculus books, you may see this parentheses notation to represent vectors. So just so you don't get confused about it. All right. Well, how are we going to represent this vector? Well, this vector, which is going to have an initial point. Okay, let me do another vector somewhere else, right here. This is the initial point, p, x1, y1, and p, like that's p1, that's p2, x2, y2. All right. So we will represent these vectors using subtracting terminal minus initial. We'll go through that in a second. All right. However, notice how these vectors have the same length and also the same direction despite having different initial and terminal points. So that's what we mean by free quantities, right? Because think about this vector being a force, a velocity, or a distance. Yes, to go from point A to B, it takes the same amount of units. It takes the same magnitude. As if I go at another point, it takes the same. It's going to be the same force or the same velocity. So that's why we have this. We call them these free quantities because they're not tied to a particular point, as opposed to order pairs. As I mentioned before, the point 3 comma 2, it's just 3 comma 2. I cannot move the 3 comma 2 to here because that's now 1 comma 4, right? So that's not the same. And the reason why we talk about these vectors as free quantities is because, yes, we will still tie them to a particular location. What is that particular location? The origin. So we'll talk about these vectors where the initial point is the origin and the terminal point will be whatever the components of the vector. So check this out, like this. So I'm still gonna move 3 units in the x direction and 2 units in the y direction. But now the vector has been positioned to have the initial point at the origin. But still, you see these arrows are pretty much going in the same direction. Well, except the red one, I think it's a little steeper. But they're essentially going in the same direction, and they also have the same magnitude. So what do these vectors represent? Like streamlines, for instance. So if you are on a boat, for instance, and so the current of the river or the sea, it's pretty much going to be described by vectors. And at some point, you may have the same magnitude of that velocity of the streamline going in the same direction. So that's why we call this vector, this vector as free quantities as opposed to just points that are fixed to a point. All right? Okay, so notation. Any vector, say v, it's going to have components a comma b, okay? So that means like order pairs, but again they're not order pairs. So if we define a vector as a segment, a vector using two quantities, that's going to be x2 minus x1 comma y2 minus y1, essentially terminal minus initial. So the thing here is, if you still plot this same vector somewhere else using other points, you will still get the same components, 3, 2, 3, 2, 3, 2. All right? Now, this other special vector, it's what we call vector, where we have that's OA. Let me call it OA. What's O? Well, that's the origin. That's simply going to be x, y. So this vector having the initial point at the origin, it's called vector in standard position. And we're going to be doing a lot of vectors in standard position, but still we need to have this idea as well about that you can position vectors anywhere you want. So they're not tied like to a particular position by like order pairs, for instance. So what else about vectors? So we were talking about the magnitude of a vector. I mean, the magnitude or the length or also the norm. Those of you who were in linear algebra, you learn about the word norm. That's the same as saying the magnitude of a vector or the length. So that's just, does that look familiar? Does that formula look familiar? What is it? It look like a lot like Pythagorean theorem. Where is that coming from? Well, not so surprisingly. So x, y, that gives rise to a right triangle, isn't it? So really, this length of the vector is the length of the hypotenuse of the triangle projected by those two displacements in the x direction and the y direction. All right? And more notation. The zero vector is denoted by a zero, not just the number 0. It's the 0 with an arrow at the top. Oh, I need more space. With an arrow at the top, which is really the vector with component 0, 0. I mean, like every system, like every system needs a 0. It needs a unit, like the number system. The 0, of course, is the 0. The unit is the number 1 in the world of vectors. The zero vectors is the vector whose components are all 0. And well, the magnitude of the zero vector, that's a 0. And this is a number, this is not a vector, okay? It's a magnitude. So that's about it, as far as what a vector is. So how about we fun and play with vectors? So let's consider the vector with initial point P 4, -5 and terminal point Q 1, -1. Okay. Letter A, draw the vector and draw an equivalent vector in standard position. Okay, so initial point P 4, -5. So 4, -5, so that's our initial point. Let me label that as a P. And the terminal point, which is 1, -1, so that's going to be Q. Okay, so what are we going to do? Trace an arrow indicating that it is the vector. Notice the direction. Notice I'm going in that direction because we have established initial and terminal point. If it were backwards, I would have drawn the vector the other way around. All right? They're also asking us to position this vector in standard position. Well, again, what does that mean to have a vector in standard position? What does that mean?
Starts at 0, 0.
It starts at the origin, right? It starts at 0, 0. So I'm going to go 0, 0. And then, what is that going to be? How are we going to go? Well, notice from P, I went 3 units, or rather negative 3 units in the x direction, and 4 units in the y direction. All right, so that's going to be our vector in standard position. All right. Okay, so they're asking us to write PQ in standard form. So what we just did by plotting the vector, by plotting the points, now we're going to do it algebraically, or numerically, if you will. So let's see. So that means we will represent PQ, the vector PQ, as terminal x2 minus x1 minus initial, and for the y as well, terminal minus initial. That is, okay, so careful. This is the terminal, this is the initial. 1 minus 4, comma, negative 1 minus negative 5. Careful with these negative signs. Okay, 1 minus 4, is that negative 3? And the negative 1, the smile rule, negative 1 plus 5 is 5 minus 1 equals to 4. Does that match with the components of the vector we did by hand? It's better, all right? If not, double check your signs or something. So they're asking us to find the magnitude. What that is, how far, how many units are there from point P to point Q? And again, that's simply, well, there's a formula for it, but in the end, it's just a result of Pythagorean theorem. That's all it is, all right? And we denote this magnitude with double bars, PQ. Some textbooks use one single bar. I think our textbook actually uses one single bar. But the reason why I don't like the one single bar is because that denotes absolute value. And I mean, I see why, because in the end it's a magnitude. And magnitudes, which are distances essentially, cannot be negative. So in a way, there's a relation between this absolute value thing and the magnitude of the vector. But to make it more unique, many other textbooks use the double bar, which is what I prefer using. All right? So that is negative 3 squared plus 4 squared equals to 9 plus 16 square root, and square root of 25, which is 5, which is a nice number in this case, right? So that's an example. How do we describe a vector using the terminal minus initial? Well, so let's talk about vector operations. Of course, we can do arithmetics with these vectors, and later we will do calculus with these vectors. Take derivative, all the differentiation rules you learned back in Calc 1, integrate vector valued functions, all the methods of integration you learned back in Calc 1, Calc 2, integration by parts, trigonometric substitution, trig integration, you name it. All right? Okay, so number one, let's suppose we have two vectors, vector u and vector v. All right, and these two vectors have their own components, u1, u2, v1, v2, and c, it's going to be just a scalar here. So what can we do? We can add vectors or subtract vectors. Notice I put the plus minus here because just to abbreviate and to condense everything into one single statement, we can add or subtract. So this is what we're going to do. We will simply add the x components with the x components and the y components with the y component. It's easy as that. All right? Number two, you can multiply a vector by a constant, by another scalar. But what does that represent? So say a vector represents a force, for instance, that is 3/4, like has a magnitude of 25, all right? If I multiply that vector by a number c, for instance, that's going to multiply the magnitude of that vector by the number c. For instance, if I multiply that by 3, it's going to make that vector 3 times stronger or 3 times longer in magnitude, depending on what does that vector represent. Multiplication by a negative number. Okay, here is where it gets a little tricky, especially when we do the operations and when I use the GeoGebra applet to show you what does that mean, all right? So all it does, it changes the sign of the components. I mean, algebraically, that makes sense, right? But geometrically, what it does, it turns that vectors and sends it to go in the opposite direction, as we're going to see in the example on the next page. Okay, so to add vectors, to add or subtract vectors geometrically, there's a couple of methods: the triangle method and the parallelogram method. Okay, I'm going to show you an example where we're going to graph both versions, both methods. Okay, so now we have more than one vector. Two vectors, u equals 3, negative 1, and v 1, comma 3. Number 1, represent u plus v geometrically. Okay, you know what? I'm going to cheat a little bit, and I'm going to do it algebraically first, so we get an idea of what we are supposed to obtain. All right, so simply u plus v, that equals, okay, that's going to be simply 3, negative 1 plus 1, 3. That is 3 plus 1, comma, negative 1, comma, plus 3. Okay? So 3 plus 1, that equals to 4, and negative 1 plus 3, that equals to 2. All right. So that's what we are supposed to obtain when we add the two vectors. And by the way, this new vector we obtain, for those of you who have taken a physics course, these are called resultant vectors. So a lot of the vocabulary, notation, and type of operation that we're going to do here, if you have taken or are taking a physics course, it's going to be pretty much the same. All right. But how do we do this triangle thing and parallelogram thing? Well, so number 1, I have reserved a Cartesian plane for each method. One for triangle method and one for the parallelogram method. Okay, so the way we go about the triangle method, so first, so we plot the first vector in standard position. That is, the vector u, which is 3, negative 1, I'm going to go 3 units in the x direction and 1 unit in the negative y direction. So that's our vector u, okay? Now, in the case of the triangle method, to add the second vector or subtract, depending on the operation, in this case it's addition, I'm not going to start at origin in standard position. So here I'm going to start at the head of the first vector, and from there I'm going to move 1 unit in the x direction and 3 units in the y direction, like this: 1, 1, 2, 3. So that's going to be our terminal point, and I'm going to get this vector. So this is our vector u, and this is our vector v. Okay? All right. So let's see. How do we add these two vectors? So we are going to connect the tail of the first vector with the head of the second vector, right? So now let's have a look at the components. Well, let's label this u plus v, all right? What are the components? So that's 1, 2, 3, 4, 1, 2. Oh, aren't they the same components as what we did using the algebraic version of it? It better be, all right? So here, first vector in center position, second vector, we start at the head of the second vector, all right? And from there, we count the units, as if we had the new origin here, if you will, all right? That's how. For the parallelogram method, number 1, let me show you an animation I created in GeoGebra to add these vectors. So I have these vectors, u, okay, let me see if I can zoom them in. Okay, yeah. Let me close all this. By the way, these GeoGebra projects, I'm going to download them on my computer. I'm going to upload them to our Canvas course page, so you can download them and you can also play with them. So if you want to represent other vectors, addition, subtraction, whatever. So, okay, so I have a vector with a terminal point A. Okay, so that's a vector in standard position. So our first vector, what was that? X was 3 units, right? So A equals 3, and B equals negative 1. I'm gonna get this slider to negative 1. So the second vector, it's adding the first point and then the second terminal point. Well, so from here I need to go, what is that? What was that? 1 unit and then 3 units. And that's going to give us the second vector. Isn't that what we did by hand, essentially? So now I'm going to create a third vector, which is going to describe the addition of the two vectors. So, what is that? This one in red, right? Which matches what we did before. So, and I mean, the pretty cool thing about GeoGebra, if you don't want to use the sliders, for instance, you can drag the points, drag it to this point, and then say you want to add it with this other point. Okay, no, not this one, just that one, right? And then from there, just play with the vectors like this, you know? And so you can add other vectors and using the triangle method. All right? So let's have a look at the parallelogram method. Let me go back to the notes. For the parallelogram method, I'm going to plot both vectors in center position this time. That is, the first vector u, which is where is it? Okay, 3, -1 at the same vector, and 1, 3. So this is what we're going to do. We're going to create a parallel or project a parallelogram right here. So again, what did we get? We got the vector 4, 2. Let me plot it in red. So 4, 2. So this projects pretty much like a parallelogram here. Well, it's actually a parallelogram. Right? Well, in this case, it's a square, but there's cases in which it looks like a rhombus, like another parallelogram. I mean, other shapes, other cases of parallelograms. And I also have another GeoGebra project for the parallelogram method. Parallelogram. All right. Just discard. So here it is. All right. So I have the vectors that I already. Well, actually, I have them. Okay, that's 3. So that's 3, -1, and the second vector that is 1, 3. Yeah, 3, like this. All right. And see how this forms a parallelogram and gives us the resultant vector. In this case, again, the given vectors u and v are again in standard position, while in this case, I mean, unlike the triangle method where we use the second, where we plot the second vector on the head of the first vector. So, and again, I'm going to upload this so you can fun and play with them. I mean, you can change the numbers here and create other new vectors, maybe like this, and see how in all cases creates parallelograms, right? It creates parallelograms, and see the resultant vector. It's always going to go on the intersection of these dashed lines right here. You can drag this one if you want. So say if you want the what's it called? The resultant vector to be 8, 1. What are the two vectors that form that vector 8, 1? And so one vector would be 7, -4, and another vector would be 1, 5. All right? So you can play with this. All right? Okay, let me go back to the notes. And what's next? Oh, find u minus 2v and represent it geometrically. Okay. So here is where, number 1, we have a negative sign. That's going to be interesting. And we have a coefficient other than 1. Well, number 1, let's do this algebraically and see what we get. Okay, so u minus 2v, that equals, okay, so 3, -1 minus 2 times the vector 1, 3. So that's still 3, -1. And well, let me distribute the 2 here. It's going to be minus 2 times 1, which is 2, 2 times 3, which is 6, and simply subtract the components of the vector. X's with x's, y's with y. That's all it is. In this case, subtract. All right. So 3 minus 2, that equals to 1, and negative 1 minus 6. Careful with the signs, that's going to give us negative 7. Okay, so that's the resultant vector here. So, all right, let me plot that vector. So I'm going to go straight to the result. That is 1 and negative 7. Okay. So that's the resultant vector, but how do we go there? Well, number one, the first vector, it's still the same. And by the way, I'm going to use the triangle method for this, okay? Okay, so this will be, 3, negative 1. But what about the second vector? Remember the second vector, it's, what's that, 1, 3? So it would have gone like this, 1, 3. Okay, let me use a different color for this. All right, so that would have been, that's what we did already, all right? But how does that, what does that do and the minus sign is going to do? Number one, this means that I'm going to plot the same vector twice its magnitude, but also I'm going to go in the opposite direction. So rather than going 1, 3, I'm going to go negative 1, negative 3. That's 1. But I'm going to do this 2 times. I'm going to do this twice because of the coefficient in front of that second vector. So I'm going to do that again. Like rise over run, right? How, you know how we go rise over run when slopes, you know? Okay. Negative 1, negative 3. Oh. So minus 2v, and this is still u. All right, and this vector in red again, this is u minus 2v. You see how we got to that point as well, to that head of the resultant vector, right? So that's the graphic point of view, and also the algebraic point of view. All right, the geometrically rather. So, all right. More definitions, I mean, because vectors can be equal if the two components are equal. For instance, the vector 5, 3 is equal to the vector 5, 3. I know this is like silly, right? This is silly because, I mean, how is that meaningful? Well, it will be a lot meaningful when we get into more algebraic situations where we need to find components of other vectors using this idea. You'll see. Actually, we'll use it for other constructions in what's it called, in analytic geometry in space later. Also, two non-zero vectors u and v are parallel if there is some scalar c such that u equals c times v. In other words, if two vectors are multiples of one another, they are parallel vectors. That's what this is trying to tell us. Now let's see. Let's look at letter C. They're asking us to prove that the vector we just found in the previous part, u minus 2v, is parallel to this whole new vector out of nowhere, w equals to negative 2, 14. How are we going to represent that? Well, number one, what did we get here? We got 1, negative 7. All right? And this is vector w equals to negative 2, 14. Okay. Comparing these two vectors, did you notice anything interesting in common? What do you notice about them? Huh? It's a double of it, right? So we can factor out, I can factor out the number 2. That's going to turn into 1, negative 1, 7. Now, notice how these two vectors right here, they're the same. What changes? The scalar that multiplies that, right? Where in this case, c equals to 2. Right, so this is a vector that is twice its magnitude. Yes, it's going in the same direction. No, maybe not in the same direction. It's going in the opposite direction because it has the signs flipped. So it's still parallel but double in magnitude in the opposite direction. So those two vectors are never going to cross. All right. Okay. The next topic in Introduction to Vectors is the definition of a unit vector. Okay, so a unit vector is a vector of a length equals to 1. Okay, and again, like in any system, we need to describe a unit. In this case, the unit vector. How do we get this unit vector? So we divide the components of a given vector by its magnitude. I mean, think about your bank account. So how much money do you have? Well, okay, that amount of money is your magnitude. So divide that magnitude by that number. What are you going to get? 1, right? The unit. Same with vectors, except that we're going to do for the 2 components or 3 components later when we get to vectors in space. All right? So given v equals to 5, -3, find the unit vector in the direction of the v. Okay, so number 1, we need to find the magnitude of this vector, that is denoted with these two bars. Magnitude of v equals the square root of 5 squared plus -3 squared. That is going to give us 25 plus 9, is that 34? Okay, square root of 34. Let's leave it like this. So there is no perfect square that we can take out of the radical. In some cases we may do, but not in this case. Okay, so let's find a unit vector. By the way, notice this little hat at the top. This v. This little hat for v. This indicates that this is going to be a unit vector. Okay, this little hat means unit vector. How do we get that? Well, again, by dividing the components of the vector by its magnitude. That is, the vector we're given, that is 5, -3, divided by the square root of 34. All we do is simply divide each component by that number. If we had a nice integer that even goes into any of those numbers, then perform the calculation. But in this case, we're just going to leave it like this. 5 over the square root of 34, comma, -3 over the square root of 34. Now, your question might be, do we have to rationalize the denominators? No, that's fine. You may leave it like this. We're no longer in Math 72 or Math 60 when you first learn about radicals, or even in pre-calculus where MyMathLab or Math Excel, it's very picky about the results. So back then, if you put this as your final answer, it would tell you something like, although your answer is correct, it's not in the correct blah, 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 right? But not for Calc 3. So this time, at this point in time, it's the system, it's more lenient about it. So you don't have to rationalize anything. Okay, more about unit vectors. Okay, okay, what time is it? Vectors. I need to go back to the parallel vectors. So here, it turns out I needed to factor out not a 2, but a -2. Just so these two vectors match. Right, because yes, we had them with the opposite signs, yes, but in this case what matters is that we have to have them with the same components. What changes instead is the scalar. In this case, it's a -2. All right, so just make sure to change those components. Okay. The components and the sign of the scalar. All right, so let's talk about the special unit vectors. Well, so we're going to introduce another system to represent vectors in terms of i's and j's. Those of you who have taken a physics course or engineering courses like mechanics, like statics and dynamics, you have used this notation already, right? But I'm not going to assume everyone has. Some of you might be seeing vectors for the very first time. Well, so I'm going to assume that. Okay, so if we consider our Cartesian plane, so that is also known as the rectangular system. That is because every scaling here, if you will, regardless of the point you go, it pretty much forms a rectangle. So that's why we call it a rectangular system, because we go x and y, and each intersect at a 90-degree angle. So that's another relation to it. What about this vector, these special vectors? Okay, these are unit vectors. These unit vectors right here, which is the vector 0, 1, which is known as the vector I. All right, and we also have the second vector, which is the vector 0, oh wait, 1, 0, not 0, 1, 0, and then 0, 1, which is our vector j. Okay, that's our vector j. Well, so this is what we call the standard vectors in our rectangular system. Well, those of you who have taken linear algebra already, you do what it's called, something that's called change of coordinates or transition matrix. So for instance, what you do there is to twist the 1, 0, 0, 1, the standard set of vectors, into, say, a system, say from another universe, from another galaxy, if you will, where we don't go X and Y, where we go to 1, 1, 4, and in order to go to look at the equivalences between a vector in one universe and the other universe, there has to be an operation to go from one world and vice versa, from one universe and vice versa. What do we do? That's called the transition matrix. Well, we're not going to get into those transition matrices in this class. That's for linear algebra. What I want to say is that the easiest and simplest standard vectors is the 1, 0, and 0, 1. Every single vector that we did in this angular parentheses or brackets will be represented now in terms of i's and j. How are we going to do this? Well, so let v be a vector with initial point 1, -2, and terminal point -2, 0. Okay, express v in component form. Okay, so that is terminal minus initial. All right, so v, terminal, that is -2 minus 1, that is -3, and 0 minus -2. Careful, we are subtracting a negative, that means add. All right? Okay. Express v as a linear combination of I and j. Well, what's a linear combination? If you haven't taken linear algebra, well, we can express vectors as an addition of two other vectors with multiples that can be positive or negative, as a combination of two. You know, like when you go to McDonald's or Jack in the Box, you go combo number 1, combo number 2. Well, that's 2 sandwiches and 3 fries, or 5 sandwiches and 2 drinks, you know. Well, so we're going to express these vectors as 2 i's plus 5 j's. So that's what we call a linear combination, a linear combo, if you will. Okay? I know what we're going to do right here. It's a little weird. Okay, so let me start with v with the same vector we just obtained, -3, 2, equal to... Okay, do you guys agree that this is the result of doing -3, 0 plus 0, 2? I know this is just thinking backwards. This is not the typical operation we do. Actually, what we usually do is compress into a single result, not to expand like this. But we need to do this for a while. All right? Okay. So how about from this first vector, let me factor out the -3. That is -3 times, okay, that's 1, but 0 times a -3, it's also going to be a 0, isn't it? And likewise, I can factor out the number 2 and express this as a 0, 1, because 2 times 0 is 0, 2 times 1 equals to 2. For the first vector, 3 times a -1 equals to -3, and -3 times 0, it's still equal to 0. Where are we going to get here? Well, let's see if we can recognize these little vectors here. So this vector right here, isn't that the vector I, the standard vector I? And j, it's the second vector. This means we will express this vector as a linear combination of standard unit vectors. So not anymore, well, actually we'll be working with both notations. Now we want to express this as a -3i plus 2j. right? So we can simply go from here to here. And I actually showed you a variable vector value function at the beginning of the note using both notations. So in a way you already saw that before. All right? Okay. So what's next? So now, okay, so this is what this from here on we will be working with vectors in any notation. My preferred notation is the first one, the component notation. It's quicker to write as opposed to doing the i's and j's, the dots, and then the hats. Takes a few seconds longer, which add up in the long run. And also the component form doesn't lead to silly mistakes in comparison to the first version. You'll see later. Okay, so let's have a look at their C. So if we have a whole new vector, u equals to I plus 5j. They're asking us to express w equals to 1/2 v minus u in both component form and standard linear in both component form and linear combination of unit standard vectors. All right. So what do we have? U equals to, what's that? 1/5. I'm going to switch to component form, all right, for now. And we also have W. No, not W, it's V, right? V equals to -3 plus 2. Okay. So let's compute W. That is 1/2 V minus U equals to 1/2. Okay, let's write down the V vector, -3, 2, minus U, which is 1/5. And well, this is simple arithmetic operations. Well, let's distribute the 1/2, -3/2, 2 times 1/2, that equals to 1, minus 1/5. Okay. So, and again, x's with x's, y's with y's. Let me make this a little bigger. -3/2 minus 1, that's -5/2. And 1 minus 5, that equals -4. So that's the result of this vector computation in component form. All they're asking us to do is to use the new notation we just learned about. That is -5/2 in the direction of I, minus 4 units in the direction of j. Right? So I mean, on my MATLAB questions, you may be asked for one notation or the other one. So you may have this angular brackets with blanks to fill in. You may have these i's and j's with blank coefficients to fill in. So we're going to be using all of these notations. Okay, much have we learned already about vectors, what they are. A little bit of operations with vectors. Well, no, we're not done with operations with vectors. We just did addition and subtraction of vectors, and the multiplication we just did. It's what's that? Just a multiplication by a scalar. So we still need to do the two vector products, the dot product and the cross product. So that's going to be sections 13.3 and 4 respectively. Now let's talk about the direction of a vector. Well, here's where basic trigonometry comes into play. So essentially a vector will project a right triangle on the Cartesian plane. And in many cases the angle may be very obvious, just go with it. If it's not very obvious, well, we may need to use the inverse trigonometric function, keeping in mind their restrictions. You will see. Okay, so for the first vector, I think you recognize the numbers: -1, √3. That's going to be a pretty nice angle. Well, so let me represent the vector first. So on a Cartesian plane, that is, I'm going to go -1 unit and √3 units. So that's going to give us the vector right here. The components of this vector right here, that is -1 and root of 3. Doesn't that look like one of those special triangles from trigonometry? And I mean, we can see what the angle is. Isn't that the 120 degrees? All right, just go with that. Just go with that. Theta equals 120 degrees, or 2 pi over 3. All right. In some cases, we will go with the radian form, or in some cases with the degree mode. All right. What about the second vector? Be careful with this case. Okay. So number one, what I would do first is plot the vector in standard position. So in this case, we're going to go, okay, negative 2 units in the negative direction, and 5 units in the y direction. That's going to be this vector right here, all right? Okay. But the question here is this one of those special triangles that you know from, the special triangles or unit circle? No, not in this case. Well, how do we get the angle here in this case? The arctangent function, right? So we would use the arctangent function. So in this case, theta equals arctan of the y over x. So that's going to give us our angle. Now, here's the thing. Arctan of y, which is -5 over -2, that equals arctan of 5/2. All right? That's arctan of 5/2. If you use your calculator, well, let me go about degree mode in this case. Okay? So let me see mode. Am I in? Oh yes, I'm already in degrees. So arctan, second tangent of 5 over 2, close parentheses, and that's going to give me an acute angle. It's going to give me a number in between 0 and 90 degrees, 68 and 68.19. So approximately 68.2 degrees. Okay, let me round it to 1 decimal place. Well, just be careful on the blue letters on my MATLAB. So it might ask you to round to say the nearest degree, or the nearest 10 or 2 decimals. Just be mindful of that. Do you see the problem here? Huh? It's not the angle, right? So we need to fix this because, okay, here's the thing. Here we're using the inverse trigonometric function. So, and recall that the inverse trigonometric functions are restricted in a way that they are, so that they are one-to-one functions. Like, okay, let me go back to basic trig briefly. So this is the graph of the arctangent function, right? Whoops. Okay, so what do we need in order to define an inverse function? That the function is one-to-one. How do we know if it's one-to-one? Well, if graphically this passes the horizontal line test, right? But in this case we have a problem. So we need to restrict our domain to -π/2, 2π/2. That is, the inverse tangent function is only defined between -π/2 and π/2. That's why we're getting a number that it's not the angle coincident with the vector we have. So for this reason, so this 68.2 degrees, I need to add an additional 180 degrees in order to go to the position we are in this vector here. All right? Okay, so plus 100. In some cases you don't need. If we were given a vector either in the first or the fourth quadrant, we don't need to fix anything. All right? Nothing. But here we need to. So that equals to, what's that? 248.2 degrees. So that is the direction, that is the angle this time. Okay. All right, so okay, here is where we need to relate these vectors with the basic idea from trigonometry that actually gives rise to the trigonometric functions. Because again, vectors have a magnitude and a direction, and the part we care the most at this point is the direction part. Okay, so basic unit circle. You know how it works. The unit circle. These are points where the angle is. The points are the cosine of the angle, and y is the sine of the angle. All right. But this is not limited to the unit circle. This setting can be also described 2 points not on the circle of any radii, not just the unit circle. So I'm going to multiply this by r. All right. So say we're describing points on a circle of radius 5 or radius of 13, 17, 59, your favorite radii. So this is the radius of the circle. So that's the geometric setting you already know. All right. Now, how does that relate to vectors? Because again, doesn't that origin look like the initial point of a vector in standard position? And any point on the circle can be taken as the terminal point. So these points are now vectors. How about that? All right? So that's why a unit vector will be represented in vector notation as cosine theta I plus sine theta j, or cosine sine. Notice there's no coefficient in front of this cosine and the sine. That's because an invisible coefficient means 1. However, if those vectors are not unit vectors, they have a magnitude of a 3, a 5, 59, 93. Okay, that's going to be our number. In this case, I'm not going to use the letter r. I'm going to replace with r. It's going to be the magnitude of the vector u. All right. So that's how it's going to be represented, and we will need this because. For real life situation, that is applications of vectors to forces and velocity. There are many cases in which inclines, for instance, will be represented with these vectors here. All right. So, and oftentimes we will not be given those components of the vectors, but at least they're going to give us the angle. So if we're given the angle, then we have a vector representation given the angle and not the components. So from there we get those components. Okay. Forces and velocity amongst many other applications of vector quantities. So let's start with the basic ones. What do we have? A child pulling a sled through the snow on a level path with a force of 50 newtons exerted at an angle of 30 degrees above the horizontal. They're asking us to express this force as a vector. Okay, number one, a diagram always helps. So a diagram where we're going to have this vector 30 degrees above the horizontal. 30 degrees, and the magnitude of this vector right here, which is 50 newtons. So that's our diagram. Okay, so we're given the magnitude, we're given the angle. In this case, they're not telling us 3i plus 9j. No. We have to create the vector using the trigonometric representation, which we just discussed in the definition above. Okay, so if the magnitude is 50 degrees, oh, come on. Okay. Magnitude of V, let me call it V. 50. And you might want to skip the units, so you can put the units at the very end if needed. And then, okay, so V will be the magnitude of the vector V times cosine of the angle, sine of the angle. That is this representation we had above. In this case, if the force were 1 unit, well, then this magnitude of V1 will be just 1. But in this case, the magnitude is 5. In a way, we're describing vectors whose terminal points are points on a circle of radius 50. All right, that's the geometric point of view. Now the physical point of view is to represent that force exerted by a child by pulling this leg right on the snow. Okay, so that is 50 times the vector cosine of 30 degrees sine 30 degrees. And well, these are pretty basic numbers, so that's going to be 50 cosine of 30 degrees, that's root of 3 over 2, and 1/2. And well, in this case, you might want to simplify, essentially distribute the 50. 50 is going to go into 2 for the two components. That's going to give us 25 root of 3 and 25. So this is the vector that describes the situation, right? So that means when the kid is pulling this leg, it's applying a force that is broken up into two components. In the x direction, it's undergoing a force of 25 root of 3 newtons. In the y direction, 25 newtons, right? There's a part B right here where we will go about addition of vectors. Okay. A second child begins to pull on the sled with a force of 30 newtons. It's not as strong as the first kid, right? But in this case, at an angle of 45 degrees. So in a way, the force is going to distribute evenly when it's going, component-wise, right? And also above the horizontal. Draw a picture of the situation, then find the resultant force. So see how we were talking about resultant? That's because we will now add two vectors, and that vector is called the resultant vector. Then find the resultant force. Okay. Well, we'll talk about this in a second. Okay, so let's draw what we already have. So 50 newtons with 30 degrees. All right? Now, in force diagrams, no, I'm not going to draw the second force over here. I'm going to start like the triangle method. So I'm going to have like another horizontal here, and I'm going to do the 45 degree. The 45 degree, well, that's not 45. 45 degrees. With, what was that, 30 newtons, right? 45 degrees. And, okay, so they're asking us to find the resultant force, that is, this total force by adding the two vectors together. Okay, let me now have those overlaps. All right, so, number one, I would need to describe the second force, the force exerted by the second child, as a standalone vector. So let me call that vector W, not V. Let me call it W. We can use the same letter. Okay, so W. Okay, the magnitude of W, which is, it's given is 30 newtons. Sine theta. And well, so that is 30 times cosine 45 degrees sine 45 degrees, okay? And we'll call both cosine 45 degrees and sine 45 degrees, they're both, okay, so that's 30 root of 2 over 2 in both cases. And simplifying this will give us the vector 15 root of 2, 15 root of 2. All right, both components are going to be the same here. Okay, so now that we have described a standalone vector for the second force, they're asking us to find the resultant force. Okay, what do we get from resultant? What does that mean we need to do? Add the vectors, right? So that means we need to add, what was that? V plus W. So what do we do? 25 root of 3, comma 25, plus 15 root of 2, 15 root of 2. Yes, these number computations are going to be weird. Well, let me leave it in exact form. That is 25 root of 3 plus 15 root of 2, comma 25 plus 15 root of 2. Okay, so this is the resultant vector. Okay. Okay, guys, now here is the thing. So they're asking us to find the resultant force, but it's actually not clear about what are they asking us for. Are they asking us for the vector, or are they asking us for the actual force? Well, so since in this case it's ambiguous, we need the two representations. Number one, this first representation as a vector, and find the magnitude, because we want to know what's the strength in this case in Newton. So that means we need to find the magnitude. That is the magnitude of the vector we just found, which is the square root of this madness here, 25 root of 3 plus 15 root of 2 squared, plus 25 plus 15 root of 2 all squared. I'm not going to square the binomials, blah, blah, blah. No, I'm just going to give you the result for this. I think you guys know what this all means. So this means this is 79.36 newtons, combining the two forces together. All right? Okay, so let's do another example. Okay, so forces. 3 forces in different directions are being applied to an object, as shown in the figure below. If the system is in equilibrium, system is in equilibrium, that is, the object does not move, find the magnitude and the direction of the missing force. So we're given force 1, that is 80 pounds with a given angle. We need to be careful with the angle, careful. And we're given force number 2, that is 50 pounds and 45 degrees. So we need to find the magnitude and the magnitude and the vector representation of and the direction rather of this third vector. Okay, so number 1. Let's represent each of the forces with given information as standalone vectors first. Okay, so that is F1. That is, well, in this case, these are not unit vectors, right? So these are vectors with magnitude 80 and magnitude 50. So this will be, for force 1, 80 cosine of blank, comma, sine of blank. Okay, what would the blank be in this case? What's the angle? Careful. Would it be the 60 degrees given here? No. It's additive from the positive x-axis. So actually we are 60 degrees away from 180. Is that 120? 120 degrees. 120 degrees. All right. So this could be a little tricky. You may be given that angle, but you need to find actually the supplementary angle. Okay. What about the? Okay, let me compute this vector. Cosine of 120 degrees plus times 80. I'm just going to give you the results. That's negative 40 degrees, and that's going to be 69.28. Okay, so those are the components of the first vector, force 1. Force number 2, F2. That equals it's a 50 pound force. That's a cosine. This time this is the 45 degree, because these 45 degrees are with respect the positive x-axis. So in this case, unlike F1, we're going to go with the 45 degrees. So that's going to give us the vector, okay, cosine of 45 degrees and sine r root of 2 over 2 times 50 each. That's going to give us 35.36 for both. 35.36. Okay, so we have two vectors, but what about the third vector? How do we get the third vector if the system is to be in equilibrium? Well, for those of you who have taken a physics class or a general science class, you may remember that 2 or more vectors are in equilibrium if their sum equals to 0. Well, in this case, the 0 vector, not equal to 0, because these are vectors. So F1 plus F2 plus F3 equals the 0 vector, not equal to 0, right? Well, algebraically, we can subtract f1 plus f2 and simply find the magnitude, right, of the miss, or find the vector, find the missing vector. Actually, number one, I'm going to add these two vectors here to get negative 4.64 and 104.63. This will be, this right here will be, let me highlight it, the addition of these two vectors, okay? That way I can easily subtract the result. So f1 plus f2 equals to negative 4.64, comma, 104 rather, 0.63 plus f3 equals to 0 vector to the 0 vector. So in this case, I can simply move the vector to the right hand side of this baby equation. So f3 will be negative 4.64, 104.63. So that means the missing force right here will be represented as the vector 4.64 negative 104.63. But they're not only asking us for the vector representation, they're also asking us for the angle, that is the direction. So what do we do? Okay, the arctangent again, because I mean these numbers are not a standard angle. So theta equals to arctan of y over x, which is arctan of negative 104.63. Okay, use your calculator to get this result. Help me out here. 4.64. And if you use your calculator, you would get approximately negative 87, right? Negative 87.46. Is that what you get? Do we need to add 180 in this case? No, not in this case, because negative 87 degrees, I mean that matches with the angle going to the fourth quadrant. And also this result is in the range of the arctangent function. So we're good in this case. Unless our missing vector were in the second or the third quadrant, well then we needed to adjust accordingly. All right? Oh, don't forget the degree symbol. Okay. Yes.
What is that symbol you're writing as you finish each problem?
Oh, that's my way to box the answers. Yep. All right. Another example, and that's the end of the section, by the way. So also, let's have a look at a velocity problem. What do we have? A plane traveling at a fixed altitude with a negligible wind factor. Otherwise, the problem gets more complicated. So the plane is traveling at a speed of 400 miles per hour with a bearing of 50 degrees west of north. Careful with interpreting this given piece of information. You'll see. The plane encounters wind with a velocity of 80 miles per hour in the direction due north. What is the resultant speed in the new direction of the airplane? So of course that crosswind is going to, well, because it's going to the north, so it's going to push the airplane in a way, it's going to make it go faster, but it's also going to shift it slightly to one side, meaning we will see. So, okay, give your final result correct to the nearest tenth of a unit. So they're asking us for the resultant speed and the direction. So in a similar way we did before. So number one, let's represent this graphically. So number one. Okay, so we have an airplane going 50 degrees west of north. What does that mean? West of north means that we're going to go to the north, which is actually what a radar on an airplane points. So that's why they use this as the standard position, you know, the positive y-axis. We're going to go back to the positive x-axis. You'll see how is that going to work this time. Okay, so that's from here and 50 degrees to the west, right? West, that's west of north. All right, so that's the vector that describes the direction and the speed of the airplane. And then there is a second vector, that is the wind, which is a vector pointing towards the north with 80 miles per hour, like this, all right? So that means our resultant speed will be like that. So that means if the airplane is going in this direction, that crosswind is going to move the airplane slightly to its right. All right. So that's what's going to happen here. Okay. So let's represent these two vectors. So I'm going to use vector with a lowercase p for the plane and w for the wind. Well, the magnitude, which is 400 cosine of the angle, which is, would it be cosine of 40 or 5 or 50 degrees? No. So here is the thing, and be careful with this part right here. Yes, so the radar information is telling us 50 degrees west of north. So that's the standard position on the radar. However, when representing this as a vector mathematically, we need to keep in consideration this other 90 degrees. So 50 plus 90, that's going to give 140 degrees. Sine 140 degrees. All right. So this will give us, after computing this, you want to check it on your calculator, negative 306.41 to 57.12. And what's that? What's next? 80. In this case, what's that? It's going towards the north. I mean, you might want to represent it using trigonometric functions because the north means 90 degrees, or simply 0, 1. However, I'm going to do the trig representation. Cosine 90, still cosine 90 is 0 and sine 90 is 1, right? And well, that will be after simplified 0, 80. So the resultant vector, I'm going to add these two vectors together. That's going to be p plus w. Both are vector quantities. So that's negative 306.41 and 257.12 plus 80. That's going to give us 337.12. So that's a resultant vector, right? So that's the vector in green, by the way, that goes from the tail of the first vector to the head of the second vector. That again, I'm going back to the triangle method in a way. So, okay, so that's the vector representation. But again, it's not clear about what velocity do we want? Do we want it as a vector, or do we want it as a module or as a magnitude? So we want to know how fast it is. So if someone asks you, how fast is that airplane going? You're not going to go, it's going negative 306.3. You're not going to tell someone a vector quantity, right? So you need a more known kind of number. That is in terms of a magnitude. That is, and in this case, that's what we call the speed. That is the magnitude of p plus w. And that's the square root of this madness here. Negative 306.41 squared plus 337.12 squared. This is going to give us approximately 455.6 miles per hour. So if you compute all this madness on your calculator, you should get that number. All right? So how do we know this makes sense? Well, so it's like a tailwind. It's pushing the airplane, making it go faster, and the numbers, the result actually confirms that, right? Unless the wind went in the opposite direction towards the south, that would push the airplane back, slowing it down, right? You can repeat that exercise by changing this to this 90 to 270 instead. That will be a wind going in the south direction. Okay, what's the direction? It's no longer 50 degrees with respect to the y-axis, that is with respect to the radar, so it's going to be a different angle. So that'll be, okay, arctan. So theta equals arctan of, that's y over x. So, which is arctan, what's that? 337.12. And over, what's that? Negative 306.4. That's going to give us approximately, initially that's going to give us a 47.73, right? However, we have a problem with this. That's because that's an angle in the first quadrant. That's because of the arctangent function. The arctangent function will output angles between the fourth quadrant and the first quadrant. And notice how that result is in the third quadrant instead. So that's why we need to add 90 degrees to fix the problem. Not 180 degrees like the previous case. In this case, just a 90 degrees. 180 would have been if we were in the third quadrant. All right? Okay, so that actually equals to 173.73. All right? And with this, we finish our first section, section 13.1. All right? Okay, let's go about section 13.2, that is vectors in space.